Okay, and our third speaker is going to be Cole.
Thank you. Seems like this thing is on. All right, I'm here to present on our paper, CCLemma. My name's Cole. Like our chair, you don't have to concern yourself with your last name. Know that I can't pronounce it either. The unfortunate woes of being monolingual. So to motivate our paper, I'm actually going to talk through a little bit of background right now on equational theorems. And hopefully I can kind of gloss over this. The first thing that we're going to talk about is data definition for natural numbers in piano arithmetic. This should hopefully be familiar. I think we saw it in a couple of talks previously. Either they can be 0 or the successor of some other natural number. When you have a definition, one natural thing we might want, pun unintended, is to have a definition of addition. And this is just a standard definition. Hopefully it's familiar to most of you. Now, the title of this slide is Equational Theorems, so I actually want to show you an equational theorem. And this one should be, I don't know, hopefully fairly intuitive. Like in grade school, we learned that adding two numbers, the order of that operation doesn't matter. And this is what the theorem states, that addition is commutative. It turns out that this type of theorem, though non-trivial, it's not immediately implied by these definitions, is a theorem that we can automate. There exist automated theorem provers that can prove this by induction, even though they're not necessarily able to natively reason about the natural numbers. They can use those definitions to construct the proofs. The thing that I want to highlight here is that this is, though automatable, probably not a theorem that you're writing very often. Somebody's probably written it once for a library, and you hope to be that someone. But I want to talk today about equational theorems that we want to prove, and not just like the wishful thinking that, oh, I wish that I had an easy theorem to prove. The example that I want to give here is a theorem that I'm going to hide sort of most of the details about. But the basic idea is that you have some sort of function f, and you have written an optimized version of f, and you want to show that the optimized version is faithful to the original implementation. It turns out that this is not exactly automatable by any of the state-of-the-art automated theorem provers, but hopefully you would agree with me that at least when compared to this other equation, it's probably closer to the type of thing that we would want to prove. So the focus of this talk today is on this not automatable part. And what I'm going to walk you through in sort of 4 sections is an example inductive equational proof, just so we're all on the same page. And then I'm going to highlight sort of the problems with it and how we address those in our paper. So let's first start by talking about how you can make equational proofs. And for the rest of this talk, I'm going to use this as my running example. Half applied to add of x to itself gives back x. OK, so how do we construct equational proofs from this? The first thing that we can do is we can case-split variables. And this is just like how you can case-split variables in like Haskell or OCaml. Hopefully this is pretty familiar. Second thing you can do to construct your proofs is you can apply functions. And I've already shown you the definition for add. Hopefully the definition for half is not too strange. Finally, you can apply lemmas. And one lemma that we might want to use is that you can pull the successor out from the right-hand argument of addition. The other lemma, in quotation marks, that we're going to include here is the inductive hypothesis. And it's not really technically a lemma. It's kind of like a lemma with a condition attached to it. And we'll see how that condition comes up in the actual proof. So let's actually go through how this proof is going to be constructed. And we start with the equation that we want to prove. What we're going to do first is we're going to, I've kind of put off all rules over there on the top right, just to serve as a reminder. We're going to case inspect the variable x, which gives us 2 different goals here. The first is where we replace x with the successor of some x prime. And the second is where we replace x with some z. And the idea here is that if you can prove both of these goals, then your original goal is implied by the case analysis. I want to examine the goal where x is equal to the successor. And in this case, we're actually going to show you how this rewrites. And in particular, what we're going to do is we're going to take the left-hand side of this goal and rewrite it into the right-hand side. How can we do that? Well, we'll first take the definition of addition over here and reduce it. Then we'll use our helpful lemma. As you might imagine, the lemma is there for a reason. And we can reduce it a little bit further. Then finally, we can take the definition of half. And at the very end of this, we can now apply the inductive hypothesis. And I told you I would tell you sort of what the condition is about it. So we have this little condition. Maybe it's tiny over here, so maybe you can't see it. where our condition on the inductive hypothesis is that we need to use it, the inductive hypothesis states that our property is true for all x that are smaller than the x that we have over here. And so in this branch over here, we've stated that x is the successor of x prime, so our inductive hypothesis is valid, and we can rewrite this to x prime. The last part of the proof proceeds rather routinely. And at this point in time, I just sort of want to pause and give you a question to ponder, which is, if you were an automated theorem prover, how would you be going about doing that proof on the left-hand side? The rest of this talk, I'm going to take us through two key problems. I'm actually going to dwell on these problems for quite a bit. And the reason for this is that I'm kind of teeing up how the solution is going to solve it by sort of going into detail as to what the problems are. And to begin with, I want to sort of give a reminder to you all that the proof that we were constructing is actually kind of small. And in this case, it's rather easy. And spoiler alert, we're going to kind of see how this gets a little bit complicated. And I want to introduce sort of the visual language that I'm going to use for the rest of this presentation, where we have, in the successor case, we have this term on the left-hand side and this term on the right-hand side. And what we're going to do when we're doing our proof search is we're going to rewrite these terms to other terms. And actually, we no longer need to sort of concern ourselves with believing the proof. I hope you believe that the proof was correct. So I'm just going to denote this with a blob. And the way that the proof search is going to go along is we're going to rewrite the right-hand side. We'll keep on doing this process until they eventually meet in the middle. So again, this is the same proof, visualized maybe in a slightly different manner. There is, of course, a but. Without the but, there wouldn't be any talk over here. The proof is small and easy, but I'm hiding the entire proof space from you. This is sort of what the search space actually looks like. And I had to actually add all these by hand in Google Slides, so really imagine that it's 10 times or 100 times bigger. The point that you want to take away here is that it's not so trivial for us to have found our way from the left-hand side to the right-hand side. Even more so, I want to remind you that the search is done online. The space is so large that we can't store all of these terms, so we have to sort of just inch our way along and hope that they meet in the middle. Now, you might be thinking from the depiction over here, okay, well, the search space is very large, but maybe if we had a lot of memory, we could store it. And unfortunately, I'd like to zoom in on this one part of the space and tell you that that's actually not the case. In fact, there are proof attempts that can continue infinitely. And the observation that I want to make here is that if we look back at our inductive hypothesis, that inductive hypothesis is referring to our original equation, which is an equality. So validly, we should be able to take our x prime, which we know is small enough, and rewrite it to the back, sort of do the backwards thing that we did before, and expand x prime. And you'll notice here that x prime appears in the term that we rewrite it to, so we can actually keep on doing this to infinity. This is bad because it means that if we're sort of naively following down the path of well, let's just pick a rewrite and run with it, we can actually just get stuck doing this rewrite forever. Okay, so that's the problem with proof exploration. Takeaway, search space is really big. Let's talk about the second problem, which is actually perhaps more salient in the context of equational theorem proving. That's that of lemma discovery. If we refer back to our example proof over here, I want to highlight another thing, which is that we have this lemma over here. And we had been given it at the beginning of time because it helps us construct the proof, but it's actually sort of valid for us to run the proof without this lemma discovered. And a natural question we might ask is, well, how can we discover that we need it in the first place? It turns out that when you have the lemma, well, I suppose you already knew this, the proof is possible. And it turns out that sort of when you remove that lemma, the proof is no longer possible. The asterisk here, okay, so this is still an infinite search space. We still have this infinite problem, but I only have a finite amount of space to sort of demonstrate this difference. So bear with me here. Without the lemma, believe me that the proof is no longer possible. We need that lemma. We need to discover it or some other equivalent lemma. And so how do past solutions deal with this? Well, the past solution is something known as theory exploration, where we basically take all of the symbols that constitute our equation, and we're just going to start enumerating lemmas that concern them. We'll start with lemma number 1, try and prove it. Oops, that failed. That's OK. We'll just go to lemma number 2. And so when we prove lemma number 2, that's going to increase our search space. And what this sort of we think about doing here is that we've proved lemma number 2. We're now going to restart the search. And then if we can't succeed at this search, we're going to actually go and prove another lemma. In this case, lemma number 3. Lemma number 3 corresponds to some terms that aren't even in our proof search space to begin with. We repeat this process. Eventually, lemma 100 is the one that discharges our proof over here. And all's well, our proof is now possible, although we still have the problem of actually finding it. But I do want to highlight one issue over here, specifically like the issue with having these lemmas 2 and 3, which is that like they're not actually very useful to our current proof. And the reason that you can think about this is that like this kind of space that I'm highlighting here is the space that we could explore without any lemmas at all. And when we discover these lemmas, they're not actually unifying anything inside of that space. Specifically, our observation is that our lemma is not useful if they don't unify two existing proof terms. So you'll observe that lemma 3 is obviously useless, but lemma 2 does give us some new terms. The thing is that they're not actually, there's no instance where there's an internal connection. So we're not actually going to be able to make progress unless another lemma deals with these new blue terms. OK, so takeaway for lemma discovery is, again, if we can't actually find lemmas in this interior space. And I want you to think, like, if we actually had the means of enumerating all the terms in this space, if it weren't so intractably large, maybe we would be able to find better lemmas. So I'm going to take you now through the solution, having teed it up. And the big idea behind our solution here is to use a data structure that exploits symmetry inherent to our problem. That data structure specifically is egraphs. It was hopefully mentioned in the title of the slides here, and I hope that you have been waiting for this moment. So if you're not sure what an egraph is, that's OK. I'm going to kind of walk you through the idea behind it. And to do that, we're actually going to go back to this proof attempt that continues infinitely. And the thing I want to highlight here is this infinite sequence of equal terms that allows you to have this proof. In particular, you start with this term x prime. You rewrite it. Now I'm showing you the AST of the term. You rewrite it to half of add of x prime, and then you do the same thing. And if this is causing your eyes to glaze over, what I kind of want to point out here is the symmetries. Like, you have the same term appearing in the same place. And so the upshot of all of this is that if we use an egraph, and I'll explain this later, you can go from this infinite sequence of equal terms to a finite representation. Now, egraph depictions are notoriously hard to understand, so bear with me. I'm going to do my best in 30 seconds. But here's the idea. This dashed line over here is now a set corresponding to, that's going to represent an infinite number of terms. Inside of that set, known as an E-class, is a bunch of E nodes. What is an E node? Well, you can think of it as an AST node, except its children are not other AST nodes. They're E-classes. So there's this mutually recursive definition going on. That doesn't make sense, then let's at least walk through an example. I'll show you that x prime is inside of this top left E-class over here because it's a nullary E node, so it doesn't have any children. So we can just extract that term. On the other hand, we know that x prime is equal to half, which is in the same E-class. But now half has a child, which goes to this add, which is in a singleton E-class. But now add points back to the original E-class at the top. And you kind of have this choice. Like, add can either point to x prime, or its second argument is the same E-class. It can point to half. And you can sort of continue this process until you finally reach a terminating term. And it turns out that this representation allows us to represent all of the terms in this infinite sequence and more. So the takeaway over here for egraphs is that they allow us to compact the representation a lot. In particular, if we go back to our proof search, again, technically infinite space, we were not able to actually store it on my laptop's memory. But if you use an egraph representation, you can now do just that. And it turns out that the way that we can discover if a proof exists is very simple now. We can simply check to see if there's an intersection between the left-hand side and the right-hand side. And this is very fast to check on an egraph. This is basically constant time. Now, I want you to recall the second problem. And again, this is the more salient problem with equational theorem proving, which is theory exploration. And again, I want to highlight that we had sort of hoped that we could enumerate, if we could enumerate terms in this region, then we could at least find lemmas that are going to not be useless, like lemmas 2 and 3. Well, it turns out that egraphs allow us to do just that. That region is specifically just the egraph itself. And if we want to enumerate lemmas that are relevant to us, all that we need to do is enumerate lemmas that are enumerate pairs of E-classes and find terms from within them, conjecture lemmas from them. I'm sweeping a lot of complexity under the rug here, but I want you to take the big idea out, which is that we can take pairs of E-classes and find lemmas from them, rather than doing this bottom-up enumeration. Let me quickly skim through the results now. I want to call back to these two equations that we talked about previously. And it turns out that these equations are ones that are from standard benchmarks. The isoplanar benchmark, I don't know if you're not familiar with this, you might think that these are of roughly equivalent difficulty. Know that the clam benchmarks are a little bit harder because they oftentimes require lemmas. And so I'm going to show you the results of our evaluation here. Now, if you're not familiar with cactus plots, the way you can read it is that like at time 1, that means that each of these theorem provers has been given 1 second to run on each of the benchmarks individually. We just tally up how many benchmarks it can prove within 1 second. So CCLemma, our tool, is generally speaking up and to the left. It doesn't necessarily outperform the other 3 state-of-the-art theorem provers we compare against, but it's at least doing very well on these easier equational proofs. Again, you want to be up and to the left. The thing that we care about, though, is these real-world equational proofs, these optimization problems that I was talking about before. And we collated a data set of a bunch of optimization problems. And spoiler alert, this is sort of the punchline of our paper, is that when you scale to these harder problems, CCLemma ends up outperforming the rest. And it's a 50% improvement over the next best. And I guess I'll give you a sense for the reason why, which is because these are very hard problems. And the reason why they're hard problems is that they have both bigger vocabularies and bigger lemmas. And for the other 3 automated theorem provers that are just doing theory exploration, that means that they need to enumerate many, many, many more lemmas before they find the necessary ones, including many of these sort of redundant lemmas, like lemmas 2 and 3. In summary, CCLemma uses eGraphs to efficiently perform proof search and discover useful lemmas. Here are results. I'm happy to take any questions at this point in time.
All right, let's have question, and let's also have the next speaker set up while the questions are ongoing.
Hi, when you said that eGraph intersection was very fast, are details of that in the paper, or like could you comment on how that's possible?
Sorry, so you're asking how it's possible?
Yeah, like how you mentioned that eGraph intersection is approximately constant time. Yeah.
So let me make a bit of a clarification. I'm not going to zoom all the way back to that slide, but I know what you're talking about. When I say intersection, I'm talking about the intersection of 2 sets. So really what we're just doing is we're testing if 2 E-classes are the same, which is like a very sort of simple, like if you know the eGraph data structure, this is like actually a very fast operation.
I was actually about to ask the same thing.
Okay.
Oh, Simon Peyton Jones. Can I, when you're doing the lemma discovery bit,
Yes.
I think you said you take these 2 islands and you pick at random 1 out of one and 1 out of the other and try to prove they're equal.
Yeah.
Is that right? So you do you do any kind of guided choice? You just throw a dice and pick one?
So that's a great question. The paper talks about this in a lot more detail. There's like sort of 2 points to that question that I will try and like answer in 1 minute total. The first is that like what you pick from the E-class is like you said, like these are all equivalent terms. So morally speaking, you should really only need to pick one. In practice, we find that that's not the case, but there are sort of limiters that we put into like preventing us from just like, since an E-class can encode an infinite number of terms, we're not going to extract an infinite number of lemmas. So we do this sort of like size-based prioritization of lemmas that we extract. The second thing is that it turns out that a lot of E-classes are not going to be pairwise, like you're not ever going to be able to conjecture lemmas from them. For example, there's an E-class that represents X prime, and there's the E-class for the RHS that represents the successor of it. You'll never be able to prove those equal. And it turns out that you can very efficiently, using eGraph analyses, sort of eliminate a lot of these by doing randomized testing and sort of caching them on the E-classes themselves.
Okay, cool, thanks.
Can I have the speaker actually come and set up? Or yeah, great. So please do come and actually set up. We can answer one more question while you're setting up.
Yeah, Jesper Cox from TU Delft. I was wondering, do you support any higher order functions or things with binders in them?
So binders we do not support. We do have ways of encoding higher order functions. Actually, the sort of flagship example from our paper is like a functional definition of how you can do like the maximum tail product of a list if you have natural numbers in it. And we show that that's equivalent to a like more efficient way of doing it that takes OFN time instead of like an n squared approach. It's right in the introduction. I think maybe that'll clarify.
Thank you.
All right, thank you very much.